Hi, welcome back to the channel. Today we are back with another research paper named Agentic Harness Engineering, Observability Driven Automatic Evolution of Coding Agent Harness. Now, today AI agents are getting incredibly better at coding, but here's the problem. When they fail, who fixes them? Today, it's usually us. We look at the agent's prompts, rewrite it, prompt, give it a better go, tools, memory, change its workflows, and try again. But what if it could remove the human from the loop? What if an AI agent could look at its own failures and say, I know why it failed, I know what I need to change. Let me modify my own environment and test the changes and see if I actually got better. Sounds like a science fiction, right? No. Well, that's what the researchers behind this paper are trying to build. And what's even more interesting is that they are not training a model, they are evolving something called Agent Harness, the collection of tools, memory, middleware, prompts, and the components surrounding the AI agent. Today, we are going to break down exactly how this works, why it works, why the experiments are founding, and when and where this approach starts to fall apart. Let's get started. So first, what this paper is actually trying to solve. So imagine you have a coding AI agent, you give it a task. Go into the GitHub repository, find the bug, modify the code, run the test, and fix the issue. The LLM itself is only part of that systems. Around the LLMs you have system prompt, tools, selections, middleware, memory, etc. etc. All of these together forms what the paper calls the harness. The paper important observation is improving the underlying LLM isn't the only way to making a coding agent better. You can also improve the machinery surrounding the LLM. The author called this a harness engineering. And then they ask about a much more ambitious question. What if the coding agent could improve its own harness automatically? And that's the core of this paper. An analogy that makes the whole paper easy to understand. Like, think about a formula. One car, you have a driver that is the LLM, and the driver isn't the entire car. You also have steerings that are the tools, gearbox that are the middleware, dashboard that are feedback, navigation system that's the memory, driving rules that are system prompts, and etc. etc. Even if you keep the same driver, changing the machinery around them can dramatically improve the performance. And that's essentially where AHE is doing. Instead of training a better driver, the paper asks, can we automatically evolve the car around the driver? And importantly, the authors keep the base model fixed during the evolution. Only the harness changes. Why it's difficult? At first, it sounds simple. That run the coding agent, see what is wrong, change the harness and run it again, and keep the improvements. But there are three huge problems. Problem one, the harness has many different components. Suppose the agent falls. Why? Maybe the prompt was bad, the shell tools was bad, the tool description was misleading, or memory didn't contain any important lessons. The many. So the evolution agent has a huge action space. The paper says existing approaches often evolve only one thing, such as prompts, skills, or playbooks. Jointly evolving everything is much harder. Now comes the problem two. Agent trajectories are enormous. Imagine an agent working on one coding problem for an hour. It might generate thousands of tool calls, shell commands, test results, reasoning, errors, retries. And now, imagine 89 benchmark tasks. You could have millions of tokens of trajectory data. The useful information might be something like Tini, the agent repeatedly edited the file correctly but accidentally destroyed the verified state afterwards. Finding that pattern inside millions of tokens is extremely difficult. So simply giving the entire trajectory to another LLM isn't a great solution. The author therefore introduced experience observability. Now comes problem 3. How do you know which change actually helped? Suppose the iteration 3 changes the prompt, the tool, the middleware, and a memory, and performance goes from 70% to 74. What caused the improvement? Was it the prompt, the tool, the middleware, or the memory? And even worse, perhaps the change fixes 10 tasks but breaks 3 others. So the evolution system needs attribution. The author solved this with what they call decision observability. Every changes must make a prediction. I'm changing X because I believe it will fix these tasks and I think other tasks might be a risk. Then the next evolution checks whether the prediction was actually correct. And that's a very important idea in this paper. Now the author called their system Agentic Harness Engineering, that's AHE. The whole system is a closed loop evolution process. You can visualize it at coding, agents, harness, run benchmarks, agent trajectory, that debugger, and all these things. Now, that's really a clever part. The authors just don't build one feedback loop. They build three different observability layers, the three pillars of AHE. And this is probably the most important sections. Component observability, experience observability, decision observability. Let's understand each one. Pillar 1. The author used NextAU framework. Instead of having one giant tangled agent configurations, they expose different harness components as separate files. There are 7 component types: system prompts, tool descriptions, tool implementations, middleware, skill, sub-agents configurations, long-term memory, and this is extremely important. Now imagine how your agent fails because it doesn't protect a successful verified state. The evolution agent can say, this looks like a tool middleware problem. Then it modify the appropriate component. Instead of modifying a 500 line prompt and hoping for the best. So why these files are mattering so much? Suppose you have a harness, including all these things: system prompts, tools, middleware, skills, subagents, and memory. Now every modification can be tracked. For example, iteration 3 in this middleware is execution risk hints middleware. The system can then use git style commits and rollbacks. So if an edit makes worse performance, undo that file change. And this gives AHE file level rollback. Now, the authors deliberately start with a very minimal seed harness. One shell execution tool. No middleware, no skills, and no subagents. Why? Because if they started with a sophisticated harness, they would know whether their later improvements come from AHC or from the original harness. Now, we have another problem. That's the coding agents generates enormous trajectories. So AHE uses an agent debugger. Think of it like another AI whose job isn't to solve the coding task. Its job is to study what the coding agents did and figure out why it succeeded or failed. The raw trajectory gets transformed into structured evidence. Instead of 10 million tokens to what happened, we get better more like benchmark, task, trajectory, root cause, success failure patterns, and then evidence. The debugger creates per task analysis reports and then benchmark level overview. Now, the original traces remain available for deeper inspection. This is called progressive disclosure. The evolution agent doesn't have to consume everything immediately, it can drill down unnecessarily. So, why this progressive disclosure is clever? Imagine debugging your own code. You don't open every file in your computer. You start with the application crashes. Then the database module is involved. Then the function is causing the problem. Then this particular line is wrong. EHE does something similar with agent trajectories. Instead of forcing the evolve agents to read millions of tokens, it gives it high level overview, task level report, relevant trajectory, specific message or a tool call, and this makes the evidence manageable. Now comes pillar 3, the most important part. The evolve agent reads the evidence and decides what should I change. But EHE doesn't allow it to simply say, I think this is better. Instead, every change must have a prediction. For example, the change is add publish state guard. Now the evidence is Agent modify verified files after successful testing only. So the root cause was no mechanism prevents post-success destructive commands, and the prediction is fix task A, B, C, D, or a potential regression task E. Now the next iteration happens, and the system asks, did A, B, C, and D actually improve? Did E actually regress? And if yes, the prediction was useful. And if no, the change can be rejected or rolled back. And the paper calls it a falsifiable contract. Now, this turned the self improvement into an experiment. Like normally, an AI says, I changed the prompt because I think it will work better. This is subjective AI. So AIG turns that into I change this specific component because I observe this specific failure and I predict this specific task will improve. Then experiment, measurement, attribution, rollback. This is the formula like the looping system. So AIG isn't simply AI changing itself. It's closer to AI performing control experiments on its own environment. Now this paper gives an explicit algorithm. Let's translate it step by step. Start with harness H0, the minimal seed harness. Run the coding agents, that's the step 2. That's run the benchmark task several times. Then record what happens. That's collecting the trajectory. Now clean the trajectory. That is normalize them into a consistent format. Step 5. Attribute the previous changes. It means compare the new results against the previous iterations, then determine which previous edits actually help or hurt. And the last step is roll back bad adapts if a modification wasn't useful, then revert it. Now run the agent debugger, extract the root causes like what useful patterns it has, evolve the agent reads what the evidence and modify the harness, then record the prediction, like every modification gets a manifest entry, then commit that store the new harness version, and if it beats the previous best harness, keep it as the best version and then repeat. So the author doesn't just run each task once. They use k is greater than equals to 1 rollouts per task. Why? Suppose one task succeeds once and fails once. That gives you more information than it succeeded. You can see that task is unstable. Multiple runs therefore provides a stronger signal for diagnosis and helps stabilize the pass at the rate one measurement. This is like what the paper is what this like exactly discovering the AIG discovered. So after 10 iterations, AIG produced concrete harness modifications like contact first workflow. In this, the agent was established and encouraged a contract before modifying things, along with a tunable shell timeout. That's publish state card. After the agent receives a verified successful state, the harness protects that state. Now, the cross-step risk monitor, which is middleware watches a sequence of commands instead of treating each command independently. Now, post-success hard block. After successful verification, risky actions again are restricted. These changes were distributed across prompt tools and middleware rather than just being a modification prompt. Now, let's get into the numbers. The authors use terminal bench 2. There are 89 tasks consisting of 4 easy, 55 medium, and 30 hard. They use 1 hour timeout per task. The primary metric is pass at the rate 1. In simple terms, how often does this agent successfully solve the task on its first evaluated attempt? Now, the result was the initial next AU seed achieved 69.7%. After 10 AHE iterations, 77, that's a plus 7.3 percentage points. And importantly, this surpasses this. You can see. So the paper claims isn't we trained a better model. It's we keep the model fixed and meet the environment better around it. So the authors compares AHE against two types of approaches. First is human designed harness such as codecs and self-evolving methods such as ACE training free GRPO, and the difference is that ACE and TFGRPO primarily operate at the prompt, playbook, trajectory level. AHE can modify tools, middleware, memory, prompts, skills, subagents, and this broader action space is where the authors believe much of the improvements come from. Now, does AHE just overfit to terminal bench? This is the second major research question. They take the final AHE harness and freeze it. Then they move it to SWE bench verified without doing another evolution cycle. There are 500 tasks across 7 repositories. AHE get 75.6 versus AHE 75.6, TFGRPO is 74.2, next AU0 is 75.0. But something else is even more interesting AHE uses. That's 461k tokens trial versus 526k for the seeds. So it is not only slightly more successful, it is also more token efficient. And like, why is lower token usage important? You will say this. So imagine two agents. Agent A solves 100 tasks in which 75 solved for 500k tokens per task. And agent B solves 100 tasks in which 76 are solved and uses 460k tokens per task. Agent B is more attractive in a real production environment. Why? Because inference costs money and coding agents can consume huge number of tokens. And the paper argues that encoding usual behavior into tools, middleware, and memory can avoid repeatedly explaining the same behavior through the prompt. Now, the authors ask another interesting question. What happens if we take the evolved harness and put it around the different models? They test GPT 5.4 Medium, GPT 5.4 XI, Quinn, Gemini, DeepSeek, and AHE improves every single of them. They gain the models like the gains are included here. Now, the biggest gain is in DeepSeek, that's a 51.7% to 61.8. That's 10.1 percentage point. And what does that tell us? The authors interpret that this as evidence that AIG isn't merely learning and how to make GPT 5.0 behave better. Instead, some of the improvements are more general coordination patterns. For example, don't destroy a verified state or watch for risky command sequences. Those principles can help different models. The paper argues that less saturated models may benefit more because they rely more heavily on these coordination mechanisms. That's why. But which part of this harness actually matters? This is exactly another fantastic experiment. The researchers take the final AHE harness, isolate individual components, they test seed memory only, seed plus tool only, seed plus middleware only, seed plus system prompt only, and results are these. Now this is very important results. And the surprising result, the system prompt alone got worse. You might expect better prompt means better agents, but the experiment says seed 69.7% and system prompt only 67.4%. So the evolved system prompt actually makes the agent worse when isolated. Why? Because the prompt was designed to work together with tools, middleware, and memory. The author explained that the cross-level strategy depends on the other component being present. This gives us an important conceptual lesson. A good agent isn't necessarily a good prompt, it's a good system. Now, the components don't simply add together. Like this is another a subtle findings. You might think Memory is plus 5, tool is plus 3, middle is plus 2. So, therefore, all three are plus 10. But that's not what happens. The individual improvements can interfere with one another. The paper says the positive single component improves some to 11% points, while full AHE improves only 7.3%. Why? Because components interact. For example, memory might encourage extra verifications, middleware might also for verifications, system prompts might additionally tell the model to verify. Together, the agent may spend too many turns repeatedly checking things. So, good components individually don't necessarily make a good combinations. This is one of the limitations of automatically evolving complex agent systems. Now we get to one of the most intellectually interesting part. Every iterations the evolve agent predicts these tasks should improve and these tasks might regress. The researcher checks whether those predictions were correct. For fixed predictions, precision is 33.7, recall is 51.4%. And compared to random baselines, which is 65.7, 6.5 precision and 10.6 recall. So the agent is significantly better than random at predicting what its changes will fix. But there's a problem. The agent is much worse at predicting regressions. Regression predictions precision is 11.8% and the recall is 11.1% on a random baseline where precision is 5.6% and recall is 5.4. So it's better than random but not by much. This means the agent is reasonably good at saying, I think this change will fix X, but not good at saying, I think this change will break Y. Why does this matter? Because this explains why the evolution curve isn't perfectly smooth. Imagine iteration with 1 is at 69.7%, iteration 2 is 71%, iteration 3 is 73.73%, iteration 4 is 72%, and iteration 5 is 75. Why can performance go down? Because an edit can fix 10 tasks plus break 5 other tasks. The agents may correctly predict the 10 fixes but fail to foresee the 5 regressions. That's why the paper identified regression foresight as one of the biggest areas for future work. So, what is the real contribution? I wouldn't describe the paper contribution simply as an AI that improves itself. That's too vague. The most acute contribution is a framework for making coding agents harness observable enough that another agent can systematically evolve them. The three things they make observable are what can I change? Component observability. What did the agent experience? That is experience observability. And did my change actually work? That is decision observability. Together, components what can change, experience what happened, decision did it work, and this leads to better harness, and then repeat. This is the heart of the paper. Now, what makes AIG different from simply doing RL? That's another question. This is worth explaining carefully. Like the traditional models, improvement often looks like data, training, better models, but AIG is more like fixed model, run task, observe failures, modify the harness, run it again, and keep useful changes. So instead of changing the weights, AIG changes the external structure surrounding the model. The paper explicitly positions harness evolution as complementary to model size training. And the deeper idea behind this paper is there's a very interesting philosophy underneath this. So today AI agents often look like LLM, huge prompts, tools, memory, random engineering tricks. Now, AIG suggests that we can create the surrounding systems as something that can learn from experiences. So instead of we build an agent, we move towards we build an agent that continuously improves its own operating environment. And that is a much bigger idea. But the paper is not claiming fully autonomous AI self-improvement. This distinction is important. The author explicitly acknowledged these limitations, like the EHE has constants. The evolution happens only on terminal bench 2. The transfer is tested on SWE bench verified. Broader programming languages aren't tested. Repository scales production deployments aren't tested. Humans in the loop workflows aren't tested. And the operating point was turned around GPT 5.4 high. The governance, guardians, the system isn't complete, and the authors explicitly describes EHE as a controlled research prototype rather than just a mature autonomous self-improvement system. Now, the evolved agent isn't allowed to cheat. It can modify the harness workflows, but things like benchmark runs, verifier, tracer, LLM configurations are read-only. The seed system prompt is also protected. This prevents the evaluation agents from doing something like I'll just disable the benchmark verifier, or I'll switch to a better model, or I'll increase the reasoning bucket. That would make the experiment meaningless. Now, if I would entire paper to someone, I would tell like we have an AI programmer. The AI programmer has a brain, the LLM, but it also has an environment around that brain that store memory instructions, memory, middleware skills, etc. And that environment is called the harness. And usually humans manually improve that harness when the agent makes mistakes. The researchers ask, why can't another AI analyze those mistakes and improve the harness automatically? And the problem is that the agent generates enormous amount of experience. The harness contains many different components, and it's difficult to know whether a particular change can adopt actually help. So they introduce the key three kinds of observability. First, make every harness component explicit and editable. Second, convert a huge agent trajectory into structured evidence. Third, force every modification to make a predictions about what it will fix or break. Then they repeatedly run the benchmark, analyze the failures, modify the harness, measure the results, and roll back bad results. After 10 iterations, the system improves from 69 to 77 on a terminal bench too. And the interesting part is that improvement isn't just in the prompt. Tools, middleware, and the memory are the major contributions. The final harness also transfers to other benchmarks and other models. So the paper's central message is don't only make the model smarter, make the system around the models learn from experience too. That's the core of the paper. Thank you for listening. It's around 30 minutes and I'm already exhausted. See you in the next one. Bye.